Chapter 6, Applications of Integration, starting with Section 6.1, Numerical Integration. All right, so areas under the standard normal curve are used for probability calculations in statistics. And the formula for the standard normal curve is given by y equals e raised to the negative x squared over 2 divided by the square root of 2 pi. And a graph of that is shown over to the right. And notice that's a bell-shaped curve. So let's set up a definite integral to find the area bounded by the graph, the x-axis, the line x equals negative 2, and the line x equals 2. So x equals negative 2, we can add that to the graph. X equals 2 is here. We've already got the graph drawn in, and we've already got the x-axis drawn in. So the area they're talking about is in between those two blue lines I just drew and underneath the curve. So there's an okay job of shading that right there. That's the area we're looking for. So if we wanted to set that up as a definite integral, we would go from negative 2 to 2, and then we'd put the function that's representing that bell-shaped curve so we could get the area underneath it. So that would be e raised to the negative x squared over 2, and all of that over the square root of 2 pi, and then we would need dx. So if we were going to find that, we would want to find an antiderivative. And there's a couple issues with that. One of them is we haven't talked about antiderivatives of the exponential function where we have a base e, or any exponential function for that matter. And it turns out that even once you have done that in Math 2, you still won't know an antiderivative for this function. With all the math I've done, I still don't know an antiderivative for this function. To the best of my knowledge, nobody has found an antiderivative to this function, and yet the area underneath this curve is critical for doing statistics work. So somehow we need techniques to help us find areas under curves even when we can't find an antiderivative. So for definite integrals such as the one above, where we can't find an antiderivative, we need numerical integration techniques. So we're going to look at 4 different techniques in this chapter, and we'll start off with the midpoint rule, which is actually one we've already done, because when we did Riemann sums, we did them with a left endpoint, a right endpoint, or with a midpoint, and the midpoint rule is just doing that Riemann sum with midpoints. So this is the simplest rule to understand because we've already gone through it, but it's not that easy to compute. None of these are, sadly, but it's also the one with the largest amount of error typically. So even though this is a nice easy one to understand, it's not one we would want to use most of the time because it has a little bit too much error in it. But the idea is just to calculate, if you want the area from a to b of f of x dx, you could calculate an m sub n. So where n is the number of rectangles that you would use. So we have a picture here showing the idea, and remember that when you're doing the midpoint rule for any given interval, and let's go ahead and just highlight one of those intervals. So if we take this interval with this rectangle, we would, if we're using the midpoint rule, we would find the area of that rectangle by doing base times height, where the base is the distance across the bottom, which would be delta x, and the height we're going to compute at the midpoint when we're using the midpoint rule. So we'd find the midpoint between its two boundaries, find the height of the function right there, which is represented by this little dot up here, and take that height times delta x, and we'd have that rectangle. And if we wanted to approximate that across, we would add that up for all the rectangles. So we do the addition of all those height at the midpoint times the width, which is delta x, all the way across, and we would call that the midpoint rule, or m sub n. And like we talked about before, if you're using the same delta x all the way across, then you can simplify this a little bit by factoring the delta x out to the right, and just say that the process is to take the height at the first midpoint plus the height at the second midpoint, and just keep doing that until you get to the height at the last midpoint for the last rectangle, which would be f of m sub n. And then once you've added all of those up, then you could multiply that by delta x afterwards instead of multiplying each individual height by delta x. All right, so that's our first technique. Let's turn the page. We'll see a couple other techniques, and then we'll start getting some practice. All right, our next rule is called the trapezoid rule, and this one helps to reduce the amount of error, but it can be messier to calculate. So the way it tries to reduce the amount of error is instead of just doing a rectangle with a flat top, since a lot of times we have slanted curves, the idea is for any given rectangle, take the height at the left and the height at the right and connect those two with a straight line. And then when you find the area underneath that, you're doing the area of a trapezoid. And the area of a trapezoid is 1/2 times the sum of the two bases times the height. All right, so where are all those pieces here? Well, this trapezoid, the parallel sides are the right-hand side and the left-hand side. Those are our bases. So you got to kind of think of this as a trapezoid that's tipped over. So its height ends up being this delta x piece. The bases are the height at the left endpoint, at the right endpoint, and then we have the half as part of our formula. So if you do that for every one of them, this is what you end up with. The area, let's look down here together. So the integral from A to B, so the area under that curve from A to B can be approximated by using these trapezoids. And so what you're going to see is you're going to see the half the height of the left-hand endpoint. So that's this one right here. So the height there, you're taking half of that. And then we have the height at the right-hand side. We also do 1/2 on that one. So you see that over here at the end of the formula. But in the middle, you'll notice that none of them have the 1/2 on their heights. So if you look at the formula, it's left plus right over 2, the over 2 being the 1/2 times delta x. So they all have the 1/2. So why don't we end up with 1/2s in the middle, right? Notice there's no 1/2 here, there's no 1/2 here, and there's no 1/2 on any of the parts in the middle if we were to write those out. So why not? Well, because as you go across and you are adding these heights, you end up with the left height and then the right height for this rectangle. And then when you go to do the next one, let's switch colors, you get left height and then you get right height. So notice that at x1, I had a blue line a minute ago and I just drew a red one over the top of it. That's because at x1, that's the right side of the first rectangle, but it's the left side of the second rectangle. So it ends up getting added twice. Each time it has that half, but if you add it twice, you get 2/2 or the whole. So that's why the middle pieces on the trapezoidal rule do not have the multiplier of a half. So that's the reason. And then the other thing to note is that's kind of nice for us because we don't want to have to do that 1/2 over and over again when we're computing these. And we've done that thing right away where we just factor the delta x off to the side, which again is this height part of the trapezoid rule. So just like we have an L sub n for Riemann sums at left endpoint and R sub n and M sub n, if we're going to use the trapezoidal rule, we can call that T with a subscript of n. So if they say T8, we'd be doing 8 intervals and doing the trapezoid method. All right, so we'll look at an example of that one in a minute. We're going to go ahead and look at all 3 of the types first. So let's look at the final type. This one is called Simpson's rule. And for this one, we kind of say, you know what, going back to doing that slanted line on the top, that was kind of a good idea because it matches up with the curve pretty good. But the curve has some concavity to it. It's bending, right? So if you look at sections like right here, there's a decent gap between the slanted line drawn in red and the black surface of the curve. And that's caused by the graph being concave down there. So if we could match it with something that had some concavity, maybe we would have less error. That's the idea of Simpson's rule. So for this one, we approximate the top of the curve with a parabola because the parabola can have concavity to it. And we also choose a parabola because it's a quadratic function that we know how to find an antiderivative of. And then we use that for the top of each section, and then we find the area under that. And this can greatly reduce the amount of error that happens, but it also increases the complexity. However, when you boil it all down to a formula, it turns out that it's not that bad. One thing just to mention, by the way, is when they do the parabolas, they do them over 2 intervals. So they use the left endpoint, and then this endpoint, and that endpoint, and they do a parabola to fit to those three. So in order for the process to work for Simpson's rule, you have to have an even number of rectangles so that you can always use two of them at a time to create your parabolas. I know that sounds all pretty intimidating, but it is already boiled down to a formula for us, and we just have to use that formula. So here's the Simpson's rule formula. Suppose f is defined and integrable on a to b. The Simpson's rule approximation for that integral using n equally spaced subintervals on a to b is given by s of n, but what we're going to write instead is like we do our tn and our mn, we're going to write s subscript n, it'll mean the same thing, comes from, so what do? We have a delta x sort of thing that we factor off to the side, but it turns out that for Simpson's rule, you have to use a delta x divided by 3. And then on your first piece, there's no 1/2. It's just to the first power, or times 1. And on the second one, you get a times 4, and then times 2, and it goes back and forth between 4s and 2s until it gets to the end. And at the end, you end up just using a 1 again. So a little bit awkward. It actually is a kind of 1-4-1 pattern, but again, you have the right of the first parabola lines up with the left of the second parabola, and so even though they're both a 1, they add up to give you the 2. You don't have to really work through all that detail, but you just have to remember that it goes 1-4, and then it goes 2-4, 2-4, 2-4 all the way through until you get to the very end, and the last one is a 1 again, because the first one and the last one aren't doubling up, so that's the reason. And then we have our formula for delta x, which we're familiar with already, b minus a over n. And then they even give us a reminder of how to find the different values of x from x0 to x1. And we'll see an example of doing that as we head off into the next part. All right, so let's go ahead and move on to our first example. We're going to try to approximate the definite integral from 2 to 4 of 1 over x dx by using each of the following. We're going to end up doing m4 and t4 and then s4, and then I'll throw in a fourth technique after that. But just a quick discussion of like why not just do this definite integral the normal way. Let's try it, and then I'm going to erase this, so be careful with what you write because it's going to need to be erased in a minute. But if you're trying to do this definite integral from 1 over x using antiderivatives, the first thing you would do is you would rewrite it as x to the negative 1, and then you would try to use the power rule, and you would add 1 to the power and divide by the new power. But if you do that, you get x to the 0 over 0, which is undefined. So if you go back and look at the power rule, you'll find out that it works for every number except for x raised to the negative 1. Now, it is actually possible to find the antiderivative of 1 over x, but we don't do that until Math 2. So at the moment, we're stumped on it. So if we wanted to find the area underneath this curve, we would have to do it using the various numerical methods. So I'm going to go ahead and show you those, starting with m4. So let's start off by calculating our delta x. So delta x would be b minus a, 4 minus 2, divided by n, which is 4. So that's 2/4 or 1/2, or I'll go ahead and put a decimal for that, 0.5. And then you want to think about what would your midpoints be for the 4 rectangles. So let me draw a little number line here, and let's say we started out at 2, and the right-hand side was 4. If we cut that in half at 3, we'd have 2 subintervals. If we cut it in half again at 2.5 and 3.5, now we would have the 4 subintervals. So our midpoints, where we would calculate height, would be here, 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 and there. So let's make a list of what those are. If you're halfway between 2 and 2.5, then that first midpoint would be 2.25. And then from there, you can just start adding the delta x of 0.5. So your second midpoint, add the 0.5, would be 2.75. But notice that does seem to match up with what we see. That's right in between 2.5 and 3, so 2.75 makes sense. Add 0.5 again, you get your third midpoint, which would be 3.25. Add 0.5 or delta x again, and you get your fourth and final midpoint, which would be 3.75. And notice that that final midpoint is right in the middle of the fourth subinterval as we go from 2 to 4, dividing into 4 equal pieces. All right, so there they are. Now let's use that to go ahead and approximate the value of the integral. So the integral from 2 to 4 of 1 over x with respect to x is what we're looking for. We're going to approximate that using 4 rectangle areas calculated using the height for the midpoint, or calculating the height at the midpoint more precisely. And so then according to the formula, we just take f of each of those heights, so f of f1 plus f of m2 plus f of m3 plus f of m4. And then once you have all those heights calculated, you just multiply that times delta x, and that will give you your approximation. But what is the f that we're talking about? The f is whatever the function is that's inside of our integral. So if we want to squeeze that in somewhere, our f of x on this problem is just 1 over x. All right, so what does that look like then? This is a nice easy function for us to start with. Nice gentle beginning. F of m1, we need the first m1 value, 2 1/4, and we just plug that in for the x in the 1 over x function, so that ends up being 1 over 2 1/4. And then we just add, plugging in the next one. So just going through, we're going to plug in this one, then that one. And plugging in is just into 1 over x, so it just keeps being reciprocals for this particular function. So 1 over 2.75 plus 1 over 3.25 plus 1 over 3.75. And then all of that times our delta x, which for this problem is 0.5. So then at that point, we just want to go ahead and approximate it. They did tell us to go ahead and round this. They said to round to 4 decimal places as needed. So I'm just going to type all of that into the calculator and see what I get. So let's open up the calculator. And let's type that in. I'm going to do an open parenthesis because I need to add all of them together before I multiply by 0.5. So 1 divided by 2 1/4 plus 1 divided by 2.75 plus 1 divided by 3.25 plus 1 divided by 3.75. That's the fourth height. So once I have all of those, I can end the parentheses on that and then multiply it times my delta x, which was 0.5. And if I round that to 4 decimal places, that would be 0.6912. So 0.6912. And that's our first attempt at a numerical approximation. We're using numerical techniques to approximate a definite integral. Now, technically, we have done it before when we did Riemann sums, but this is the first time we've thought of it as a technique for approximating area, and now we're going to go on and jump into how does it look when you try it with the trapezoid rule or with Simpson's rule. We're going to stick with the same problem so we can just compare how they all turn out. All right, so this one is a continuation of the last problem. So we're still trying to approximate the definite integral from 2 to 4 of 1 over x dx. This time we're going to do that with t4. So let's just go ahead and start off by calculating all the little pieces we need. So let me write down here again just what is it that we're after. We're after the integral from 2 to 4 of 1 over x dx. That's what we're trying to find here with t4. So delta x would be the 4 minus 2 over 2, which would be 0.5. Same delta x as we had a moment ago when we did the midpoint rule. And then we want to think about what are all of our endpoints. And we do something a little new. We start off with x0 instead of x1. So we're going to go x0 up to x4. x0 is always just the left-hand endpoint. So we're integrating from 2 to 4. So x0 is going to be 2. And then finding midpoints is a little bit of a pain because you have to think about all of these endpoints and then think about what's in the middle. Here it's easier. Your x0 is always the left-hand side, and then you just keep adding delta x. So x1 would be 2 plus a half, or 2.5. x2 would be add another half, so now we get up to 3. x3 is adding another half, so we get up to 3.5, and x4 we add half yet again, and we get to 4. It should always be the case, if you've done it right, that when you get to the x sub whatever n was, in this case n is 4, so when you get to x4, that should be your right-hand endpoint, which is your upper limit of integration. So n was 4. Let me actually go different color here. So n was 4, and when we got to x4, we got 4, which was our upper limit of integration. And then just another reminder, our f of x is what was inside of the integral, so f of x is 1 over x. So this time we're going to try and approximate this definite integral. Instead of using m4, we're going to use t4. So how is that different? Instead of just adding all the heights, it's almost the same, but we're not using midpoints. We're going from left endpoint to right hand endpoint, and we're only doing 1/2 times f of the left-hand endpoint. And then we do the height at all the middle values. So from f of x1 to x3, so I only skipped one thing with the dot, 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 so maybe that was a little silly. But then when we get to f4, it's a 1/2 again. And then times delta x. So that's what we want to do. So we have 1/2 from that 1/2 in front of the f of x0. And then what is x0? Let's get some different colors working here. So x0 is 2. We're going to plug that into the 1 over x function. So that's going to give us 1/2. So the first 1/2 comes from the formula. So that's this 1/2. The second 1/2 comes from taking x0, which is 2, and plugging it into the 1 over x, which gives you 1 over 2. So a little tricky that those match up. They won't always. But in this case, you can see the different places those come from. So then we go to x1, and we plug that into the function. So 1 over 2.5. But when you're in these middle ones, you don't multiply by the 1/2 anymore. So then we add 1/3. And then we add 1 over 3.5. And now we're at the last one, so the 1/2 kicks in again. And we have 1 over 4, where our last value was 4. And then all of that gets multiplied by delta x, which was 0.5. So again, just kind of on the highlighting part, this 1/2 is from that 1/2 out front. So we do that on the first and the last one only, but not in the middle ones. All right, so from there, we go to the calculator and we enter it in. You could do some trickery with some sequence to kind of automate this, but I'm trying to keep the size of n fairly small for you guys on most of the problems, so I would encourage you just to go ahead and write them out like I'm doing here. And then we're going to have a good technique at the end that's kind of nice and fast. So when you're doing these, the n I'll keep it small, and I would encourage you to just write them out, and then some sequence is probably more trouble than it's worth. All right, so let's go to the calculator. And same idea. So open parentheses for the first one, and then I need 1/2 times 1/2 plus, and then I don't need the 1/2 part anymore, so just 1 over 2.5 plus 1 over 3 plus 1 over 3.5. Now I'm to the last one, so I need the 1/2 again, times 1 over the last value, which was 4. I ended the parentheses. Now I've got all of those added together. I need to go times delta x, which is times 0.5. We're supposed to be approximating the same area we were on the previous question, so we should get an answer fairly similar. And we get the same 0.69 part, but our next two digits are a little different. Looks like this time it's 0.6970. So let's go ahead and write that one down. Just a comment, it's kind of hard at this point to know which is better because we don't know what the right answer is. We will eventually get there where we know what the right answer is, and when we're all done, we'll look at the graph too to see kind of where the different errors come from on these techniques. So they're not identical because they're approximation methods. They're not giving the perfect answer, just a Pretty good one. All right, so we've seen midpoint at 4. We've seen trapezoid at 4. Let's go look at Simpson's rule with 4 now. So the delta x, the x0 through x4, the f of x, they're all the same as above. So instead of writing those down, I'm just going to jump right into the formula on this one. So we're trying to find the definite integral from 2 to 4 of 1 over x dx. This time we're going to approximate that by using Simpson's rule 4, so that will be S4. All right, so what does that look like for Simpson's rule? We need to take the height at the left endpoint plus 4 times the height at the next boundary. Then it goes back and forth from 2 to 4. Until you get to your last one, which is f of x4. And then that one doesn't have a multiplier. I ran out of room here, so I'm going to shrink this up a little bit because that's just adding, whoops, that went a little crazy. That's just adding the height part. We still need the delta x part. So squeeze that in over here. So times delta x. So now let's start plugging those in. So f of the first value is 1 over the left-hand endpoint plus 4 times 1 over the next endpoint. So that would be 1 over 2.5 for our next boundary edge, the x1. So we could put 4 times 1 over 2.5, but in this case, I'm just going to put that multiplier in the numerator. So this 2 I'll put in the numerator, and then we have 1 over x2, so that's 1 over 3. Plus this 4 I'll put in the numerator, and then we have 1 over 3.5, so we get a 3.5 here, and then plus, with no multiplier this time, 1 over the last endpoint. And a little mistake I made up here, it's not delta x, it's delta x over 3 when you're doing Simpson's rule. It has to do with like countering for those extra multipliers of 4, which are going to make things bigger, right? Somehow the over 3 balances that out. So sorry for forgetting that, but we got it back in there just in time. So now times delta x 0.5 divided by 3, and then we're going to go to the calculator and see what we get for this one. So off we go. Bring that in one more time. And very similar technique. So open the parentheses, 1 over the first one, plus 4 over the second one, plus 2 over the next one, back to the 4 again for the third one, nothing over the top, so that'll just be a 1 over the 4, and then we have times our 0.5, but we also have to divide that by 3. And again, this is a technique for finding the same area, so it should be in that 0.69 ballpark if we've done it right. So what do we get here? 0.6782. I think I made a mistake of the 1/2, 4 over 2, and then 4 over 2.5, 2 over 3, 4 over 3.8 I did. So second enter, pull that back up. Got to get in there and edit that. Second enter. This one right here should have been a 5. There we go. So 0.6933. All right, so now we've done all 3 of them. I don't know, fairly similar. I like using the trapezoid rule and the Simpson's rule a little better because you don't have to find the midpoints. So finding the midpoints is a little bit of a pain. It's nice to just start at the left boundary, end up at the right boundary, adding delta x as you go across. So I think that's a little bit of a smoother process to do that. So I prefer that, but none of them were horrible. But here's the coolest one of all. Your calculator has like an extreme version of Simpson's rule built into it, where it essentially does Simpson's rule with like n equals 1,000 or n equals 1,000,000, some number so massive that it gets all the decimal places right when it does its approximation. So if you want to find that on the calculator, let me tell you the buttons we're going to push and then we'll go do it. So you want to choose the math menu, or press the math button, and then within that the first column says math, so we want to be in there. And then you scroll down and you look for something that says fnInt, which I believe is function integration. And you'll go ahead and select that, and it'll have an open parentheses on it. And then what you do is you type in whatever your function is, tell it what the variable is, tell it what your lower limit of integration is and what your upper limit of integration is. And it will give you a Simpson's rule with a gigantic n plugged in. One we would never want to do by hand, but one that is very accurate. So we're going to do the integral from 2 to 4 of 1 over x dx, so just the same one that we did up above. So we want that to look like on the calculator fnInt. We're going to type our function, which would be 1 divided by x. We're going to tell it the variable, which is x. We're going to tell it the lower and upper limits of integration. And then it will tell us a very, very accurate answer or decimal approximation for the 2 over 4. It's so accurate that right here I put equals. If you look every other time, like when we started to do Simpson's rule, I said we were going to approximate by Simpson's rule with s of 4. But when you do that with fnInt, you're getting a super accurate, basically equal value to all the decimals that you can see. I'm only putting approximately equal over here because I'm about to round what I get to 4 decimal places. But all the decimals we see on the calculator for this one are going to be accurate. When you're in Math 2, you can test me on this because you'll know how to find the antiderivative and you can check the answer against that. But for now, let me show you how to do that on the calculator. All right, so we want to hit the math menu. So the math menu is right below the green alpha button on this calculator, and same should be the same on your TI. So I press the math button. See the columns up at the top? We've got math, numerical, CPX, PRB. So in the math columns where we want to be, on most of them it is number 9, but you're looking for fnInt. So I'm going to press the fnInt. You can just scroll down and then press enter on your calculator, or if you know it's at 9, you can just press the 9 button. All right, so I did that, and then I'm going to type my function, 1 over x, and then I have to tell it the variable, which is x, and then the next part doesn't have anything to do with the n we're using because we're not using the n of 4 anymore. We're using an n of like almost infinity in a way. So we're putting the limits of integration, so from 2 to 4. And this should come out kind of close to what the other ones did, so let's have a look, and we'll round it to 4 decimal places. So 6932 is what we get, and you can see some of the other answers, and one of the things you'll notice is the one that did the best job before, because now we're looking at the right answer. The right answer to a bunch of decimal places for this area is 0.69314711806. We're just going to write 4 of them, so 6932. But if you compare that to the other ones that we've done already, the one that was closest to this one, which is the correct to 4 decimal places answer, the one that was closest was Simpson's rule. It was only off by 1 decimal place in the 4th spot. Trapezoid rule was over by 0.0048, I think. And the midpoint rule was under by 0.30, I think. So, or maybe it's just 0.20 was under by. So actually the midpoint rule, I think, was a little bit more accurate than the trapezoid rule this time. In general, you can trust the trapezoid rule to come out a little better than midpoint, but it's not going to happen that way all the time. All right, let's go back to the calculator one more time and look at just the graph of this to kind of think about how it turned out and why we'd get the errors that we would. So let's go back, just full calculator on this one. So we'll enter in the function, which is 1 over x, and then let's set our window. So we're only going from 2 to 4, so I'll just go from 2 to 4 on this as well. And for the scale, we'll put 0.5 because then we can see all of our endpoint tick marks, I suppose. And for the height, honestly, I'm not, let's see, we're doing reciprocals, so those are going to be kind of small. So let's go from just 0 up to 1. And let's have a look at the graph. All right, so here's our graph. And notice that it's got a kind of concave up look. So if you were going to go with midpoints, and I think that'd be like right around here for the first one, but if you had a rectangle and you went with its midpoint, it looks like the extra you're missing on the left is balanced out by the extra you're getting on the right because of its kind of steady decrease. So that the midpoint's going to do pretty good. But because it's concave up, when you draw a straight line from one point to another, you're always going to be over the top of the actual curve. So we're going to always get a little bit too much area when we try and use the trapezoidal rule on something that's not changing concavity and is always concave up. You're going to end up with a bit of an overestimate. And then finally with the Simpson's rule, because the parabola has the ability to be concave up, it can lay fairly closely on top of this curve and give us the best approximation of all. So there's a quick look at the curve and the different techniques that we used. This fnInt is the all-star. It's the one that's going to be the best one for us to use when we want to have a decimal approximation for a definite integral where we can't find the antiderivative. All right, a little breaking news just in, and you probably noticed this already, but I got the wrong last decimal place on this one when I wrote it down. That was not supposed to be a 2. That was supposed to be a 4. So this is going to be 0.69, sorry, it was supposed to be 6931, not a 2. Let me go back to the calculator and show you that one real quick. It was 6931 followed by a 4, so we round down and do a 1. My brain was going too fast or too slow or too something, and I put a 2 instead of a 1. But there's the correction on that. So 6931 is your actual answer for Simpson's rule. Still not as close as I had said before. It's off by 0.0002, but still by far the closest was Simpson's rule to the right answer of any of those that we looked at. All right, here's a summary for that last technique with the fnInt. So these are the steps for approximating a definite integral from a to b of f of x dx using fnInt on the TI-84 calculator. So the first step is to press the math button. That takes you into this menu right here. This is the way it looks on the TI. From there, you want to be in the math column, which should be where it starts out. You'll have to scroll down a little bit, look for fnInt, which is number 9 on most of the calculators. And then your structure is fnInt, f of x, lower limit of integration, upper limit of integration. So the example that we just did was the integral from 2 to 4 of 1 over x dx, and that looks like fnInt 1 over x, 2, 4. So that is our process for using Simpson's rule. So there's with screenshots and some step-by-step for you to hopefully make that go a little smoother. The other thing that's going to help things go smoother for us is seeing another example. I started off with a super easy function, just the 1 over x. So I'm going to look at one that's a little messier because you have to deal with some that are a little messier when you're doing your homework. So we're going to do the definite integral from 5 to 9 of the square root of x squared plus 4. One that with our Math 1 techniques we do not know how to find an antiderivative of, so we're going to go ahead and approximate it using the different techniques. We'll round to 4 decimal places like we did before. We're going to up the size a little bit, so we're going to go with 6 subintervals, and we're going to start off with the midpoint rule, and then we'll do the trapezoid rule, Simpson's rule, and finally fnInt. So we take a look at this in all those different modes. All right, so let's start off with the M6. So for those, you want to know delta x. So you take your upper limit of integration minus the lower limit of integration divided by the number of subintervals. So that's 4 over 6 or 2/3. Do not approximate that by like 0.67 or you're going to bring in extra error into the process. So I'm going to use that exact fraction as I go through. The f of x function is going to be whatever was inside the integral. So the f of x that we're using on this one is the square root of x squared plus 4. So that's what we're going to plug midpoints into when using the midpoint rule. So the next thing to do would be to list all the midpoints. And it turns out that if you're going to do the midpoint rule and the trapezoid rule, you should probably start out by listing your endpoints for the trapezoid rule, because that will allow you to then just look at the in-betweens for the midpoint rule. So I'm going to jump down here and kind of work on A and B simultaneous a little bit. So for T6, the trapezoid rule, we'd still have delta x and it would be the same, 2/3, same formula, same answer. And then when you do endpoints, they're easier on the trapezoid rule, so that's why I'm starting down here. So your first endpoint would be whatever the left-hand or lower limit is on your definite integral. We were going from 5 to 9, so our starting point is 5. And then to get to x1, x2, and x3, and so on, you just keep adding delta x, which is 2/3. Because that 2/3 is a fraction, it would be nice, instead of starting off with the 5, if we wrote that as a fraction and said 15/3. So I'm going to do that, and it just makes it easier to add the delta x on the fly. So now x1, I add 2/3, and I'll have 17/3. And then x2, add 2/3, and I get 19/3. And I just keep doing this, adding 2/3 over and over again. Some of these can be simplified, but I'm just going to write them as they come. And then finishing this off down here, x5 would be 25/3, and x6 would be 27/3, which is 9. So remember, when you reach your n equals 6, and we just reached that right there. So, whoops, let's do the different color. So when you reach the n equals 6 right there, you should end up with your upper limit of integration, which, going back up there, to the very top, that upper limit was a 9. So we are getting a match between our x6 and our upper limit of integration, which means that we're doing things right. All right, so we'll come back and we'll use those in the trapezoid rule in a minute. But now let's come up here and list all of our midpoints. And the midpoints are just going to be right in between these values we just computed, and that's nice and easy to do. So what's right in between 15/3 and 17/3? Well, 16/3. So our first midpoint, M1, is going to be 16/3. And then you can just keep adding the 2/3 to that. So M2 would be 18/3. Nice number, but I'll just leave it as a fraction. M3 would be 20/3. And you can look down below. We just keep ending up right in the middle of the ones from before. So M4 is 22/3. M5 is 24/3. And M6 is 26/3. And the only thing I would mention about that last one is notice that it ended up right in between the 25/3 and the 27/3. It's the midpoint of the last interval, so that's great. That's what we're supposed to be getting, is midpoints. All right, from there, we can go ahead and start approximating now using the M6. So we're trying to get the integral from 5 to 9. It's of the square root of x squared plus 4 with respect to x, and we're going to approximate that using midpoints with 6 subintervals. All right, so what do we get? Well, for midpoint rule, we want to start calculating all those heights. So we take our first midpoint and we plug it into the function. And this is messy, but it's the job. 16/3 squared plus 4. And then we just do the next one. Our next midpoint is 18/3 squared plus 4. And we just keep going until we get to the last one. And our last one would be 26/3 squared plus 4. Once you've added all the heights together, you still need to multiply by delta x, which was 2/3. And then we can just go plug all of this into the calculator. Like it or not, we can go plug all of this into the calculator, and it is messy. So it may be the not on the like it or not. But let's go take a look at that. We're going to just keep adding, starting at 16/3, keep adding 2/3 to that piece, squaring it plus 4. And it is tricky, but I felt like I should show you a tricky one in the notes since you're going to have to do some tricky ones while you work. All right, so let's get a fresh start here. So I'm going to do the open parentheses that kind of represent those brackets. And then I'm going to take my first square root, so second square root. And then I need to open parentheses again because I'm taking 16 divided by 3. I need to close the parentheses there and square it. If I don't put parentheses around that fraction 16/3, I'm only going to square the denominator. So then plus 4, because that's part of the function. Remember, the function was x squared plus 4. And then I have to end the square root. And it looks like, yeah, so we're good. And then plus, now go on to the next one. So we keep adding 2/3, so we got to do this over and over again. So second square root, open the parenthesis for the fraction, so 18/3. Now that one happens to be 6, so you could just put a 6 squared if you want. I want to keep thinking about that adding 2/3, so I'm going to leave it as unreduced fractions. Plus 4, end the parenthesis, and then start again. Another square root, another parenthesis around the fraction, add 2/3, so 20/3 now, squared, plus 4, end the parentheses on the square root, and keep going. Another square root. We got to do 6 of these, so we're halfway there. Actually, we got to do 7 because we do the left-hand endpoint all the way to the right. Let's see, we're doing midpoints, so sorry, just 6 of them. 7 is coming. Great joy, right? So square root, open parenthesis, we just did 20/3, so now it's 22/3, squared, divided by, plus 4, and the parentheses for that square root, do the next square root, second square root, open parenthesis for the fraction, 24/3, end those parentheses, square that x, add 4, end the square root with end parenthesis. We've got one more to do. Second square root, open parenthesis for the fraction, we just did 24/3. So now we're at 26/3, end the parenthesis and square that fraction, plus 4, and the square root on the parentheses on the square root. Now finally end the parentheses on adding all of those heights together. Then times delta x, which was 2/3. And hopefully I get the number that I wrote down earlier. 29.1483941 is what we get. They want us to round that to 4 decimal places, so that's going to be 29.1484, taking that 3 and rounding it up because of the 9 that follows it. So there is our first look at kind of a messy midpoint rule problem. So we ended up with 29.1484. And it's messy, right? Like there's no getting around that, but we're getting an answer for a definite integral that we don't know how to get through antiderivatives. So if this was something that we needed, this is giving us a doorway into getting an approximation for that. All right, let's go ahead and move down to the T6. We've already calculated the endpoints. So let's look at what we need to do for that one. So we just kind of separate all this stuff off. So we're looking to get the definite integral from 5 to 9 of the square root of x squared plus 4 with respect to x. We're going to approximate that now by using T6. So fairly similar to what we just did. Got to do the bracket, except for now you start at your left-hand endpoint, and your first one has a 1/2 in front of it. And your last one has a 1/2 in front of it. All the others are the same. So then we're going to do the square root of, and our first endpoint is the 15/3. You could just do 5 squared for that one if you want, because that one is a nice number, or you can keep it as the 15/3. And then plus, now we don't do the half anymore. And we go to our next one, which is 17/3 squared plus 4. And we just keep going like that until we get to the next to last one, which would be the 25/3. We do that one. So 25/3 squared plus 4. And then when we do the very last one, there's a 1/2 again. And I've been a little too excited on the size here, so we create a little bit more space. And we'll finish this up. So on the 1/2 one, now we still have the square root. Our last endpoint was a nice number again, so 9 squared plus 4. And then at the end of that, we have to do times delta x, which is times 2/3. And then we go to the calculator and we enter this really messy thing. And it's about the same as the last one, roughly. We got one extra piece to do when we do the trapezoid rule. And one thing that's good news is the midpoint rule did not help us with the trapezoid rule. That's not the good news. But the trapezoid rule, if we do that on our calculator all in one piece, it can help us do Simpson's rule faster. So I'm going to go ahead and type all of this in one piece. And by the way, if your calculator is not capable of showing, I'm just going to go calculator here, of showing all this work at once, then you should see me in class so I can help you switch the mode so it can. When you're entering something this messy, it's nice to see it all at once, even if that takes multiple lines on the screen of your calculator. All right, here we go. Typing in trapezoid rule, 6 intervals. So we're going to open parentheses on the whole thing, and then we're going to multiply by 1/2 on the first one and the last one. So there's the 1/2 for the first one. And now we're just doing those square roots like we did before. Our first one is just 5 squared plus 4. If you do enter it as just 5 squared instead of 15/3, you don't need the parentheses, so that's a nice piece of doing it that way. Now on all the remaining square roots until the last one, you don't need the 1/2. So our next one is 17/3 squared. That's a fraction, so I did it in parentheses again, and then in the parentheses on the square root. And we just keep going. So second square root, and then we have 19/3 plus 4. Oops, I forgot the square. Definitely would prefer not to make a mistake. And then in the parenthesis on that one, plus our next square root. And that one is 21/3. That one is a nice number, but now that I'm kind of bravely wandering here into the middle, I want to make sure that I can see the pattern, 19/3, 21/3, and so on. And by the way, when I close this, it's saying I've finished the whole thing. I forgot to open parentheses in front of that 21. Above the stat key, there's the delete key. Above the delete key in orange, INS stands for insert. So if I hit the orange second key and then insert, I can add the open parentheses that I forgot a second ago. Very nice to be able to edit when you're doing things this messy. All right, on to the next one. Second square root, open parentheses for the fraction, 23/3 squared plus 4, end parentheses on the square root. Next one, open parentheses, 25/3, square that, plus 4, close the parenthesis on the square root. And then finally, our next one is going to be 27/3 or 9, which is the last one. And on the first one and the last one, we need that multiplier of 1/2. So I'm putting the 1/2 times here, and then my square root, and then I have 9 squared plus 4. And then I close parentheses, and that's all those heights of the trapezoid's bases added together. Now I need to do times delta x. Delta x was 2/3. Hopefully we get an answer fairly similar to the one we did for the midpoint rule. That's always a good sign. 29.15103.504. And we want that to 4 decimal places, so 29.1510. Leaving the 0 this time because the digit after it is a 3, so we're not going to round up. Bringing that back in, 29.1510. All right, there's my answer. Nice and similar to the last one, which again is always a good sign if they're in the same ballpark because they're supposed to be approximating the same area. So if you're getting very different answers for these two things, seems to indicate that something's gone wrong somewhere. Some key reminders on this one. When you're doing this, you need the 1/2 on the first one and the last one, but all the ones in the middle, you don't. Those are just the midpoint plugged into, the endpoints plugged into the function. But for the very left-hand endpoint and the very right-hand endpoint, those aren't overlapping. Those need the 1/2 on them. And then don't forget your delta x at the end. That's another place where things can go wrong. All right, we're going to go do Simpson's rule next, and I'm going to show you how we can edit our last calculator calculation when we do Simpson's rule, and that'll be nice to be able to take advantage of work we've already done. All right, so moving on to the Simpson's rule for this one. There's a lot of overlap between Simpson's rule and the trapezoid rule. So the delta x will be the same. So the delta x will still be 2/3. All your endpoints will still be the same. So we'll have our 15/3 or 5 on the left, and then we're going to go through the 17/3, 19/3, and so on until we eventually get to our last one, which would be x6 will be the 9. And then our f of x is still the same. It's the inside piece. So just a reminder, the inside function was the square root of x squared plus 4. So that's what we're going to be using on this. So we're trying to find the integral from 5 to 9 of the square root of x squared plus 4 with respect to x. We don't know how to find an antiderivative, so we're going to approximate that using Simpson's rule with 6 subintervals. So then what does that look like when we write it out? So with Simpson's rule, we're plugging in the different endpoints to the heights, and it starts with a 1, and then the multipliers go 4, 2, 4, 2, 4, 2, 4, 2, until you get to the very end, and then it's just a 1 again. So the first one's just a 1, so that's going to be the square root of our left-hand endpoint, which is 5. So 5 squared plus 9 inside the square root. Then we do the multiplier by 4, and we plug in the next one, which would be the 17/3. So 17/3 squared plus 4. Then we switch to a 2 multiplier, 19/3 squared plus 4. And then you just keep going back and forth between 4s and 2s. So now we're at a 4. We have 21/3 squared plus 4. Then we're back to a 2. 23/3 over, or squared plus 4. And then we go plus a 4 square root 25/3 squared plus 4 plus, now the next one is 27/3. And when you do that 27/3, that's 9. So you're at your last one. So instead of going back to a 2, now it's just going to be a 1 times. So just the square root of 9 squared plus 4. And then Simpson's rule is delta x divided by 3 as your multiplier. So we have our delta x, which is 2/3, and then all of that gets divided by 3. That's just 2/9. So when I go to the calculator, I'll probably just put in a 2/9. But there it is written out. So key pieces, your starting bracket and ending bracket. So you're adding all these different heights of the function together. The first one has no multiplier. The last one has no multiplier. But after that, it goes 4, 2, 4, 2, 4, and then back to 1. So it's this 4, 2 alternating until you get to the last one, and then that'll just be a 1 instead. All right, so let's go to the calculator. Hopefully we get an answer kind of similar to what we did before, and I also want to show you how we can modify what we did before instead of starting from scratch. So I'm going to take that last one, and I'm going to hit second and enter to pull it back up. And I'm going to go back to the beginning, and I'm going to start modifying it. So the first one, I don't need the 1/2, so I'm going to delete the over 2 and then just do 1 times. But all the endpoints are the same. So we're plugging in 5 and 17/3 and 19/3, 21/3, 23/3, 25/3, and 27/3 or 9. Like they're all the same things getting plugged in. What's different is just the multiplier. So I can go to where the square root starts, and I can hit that second insert and do 4 times out front of that next one. Then I can go to my next square root and hit second insert and do 2 times, and just keep alternating those. So then second insert and 4 times. And then go to the next one, second, insert, and 2 times. Next one, second, insert, and 4 times. Maybe that's a little tricky, but it's a whole lot less tedious than what we had to do before with typing it all and thinking about parentheses and all that. So if you just got it right with trapezoids, take advantage of the fact that you had it all structured right with parentheses and just make these little modifications. Remember, the last one's a times 1. So instead of the 1/2, I'll delete the divided by and the 2, and then it's just a 1 times. And then, just a reminder, it's supposed to be 2/3 divided by 3, or delta x divided by 3. So 2/3 divided by 3 becomes 2/9, so I'm going to change that to a 2/9. Hopefully, I get an answer very similar to the one above, because again, we're trying to approximate the same area on all these. And we did, so that's good. So 29.1492836, rounding that to 4 decimals will be 29.149, and then that 2 will round up to a 3 because of the 8 that follows it. So we're going to have 29.1493. So we go back and we write that one down. Let's do it in blue instead of in highlighter. So 29.1493. So there's my Simpson's rule answer. Typically, that is going to be your most accurate of the 3, but we don't know the right answer yet, so it's hard to say for sure. If you want to know the right answer to this, Math 2 to the rescue, or better yet, for us right now, fnInt to the rescue. So we're going to do the integral now from 5 to 9 of the square root of x squared plus 4 with respect to x by putting it into fnInt. So the structure of that will be fnInt, type the function, so that'll look like square root, open parentheses, x squared plus 4, end parentheses, comma, the variable, which is x, comma, the lower limit of integration, comma, the upper limit of integration. So that's what that should look like on the calculator. Let's make that happen. So we want to go into the math menu below the alpha key, stay in the math column, go down to number 9, fnInt, and then type our function. So that is the square root of x squared plus 4, and the parenthesis on the square root, comma, our variable, comma, lower limit, comma, upper limit, end parentheses, and enter for a whole bunch of digits that are completely accurate. So 29.149271116, all of those decimals are reliable when you do fnInt. They still only asked us for 4, so we'll put 29.1493, rounding that 2 up because of the 7 that follows it. All right, so for this last one, we got approximately 29.1493. All those digits are accurate. So at this point, we can have a look back to see how we did on the other ones. We'll check out Simpson's rule. Same answer. Now, if you look at all the decimals, they're not the same. Like if you go the 5th, 6th, 7th decimal. I think when I looked at this earlier, they actually differ in the very next decimal place in the 5th. But with our directions of rounding it to 4, Simpson's rule nailed it. And how about the other ones? The trapezoid rule, 29.159, so that was a little bit of an overestimate for that one. And the midpoint rule, 29.1484, that one's a little bit of an underestimate, but they're all actually pretty good. The reason they work out pretty good, if you go look at the graph of the square root of x squared plus 4 over this region from 5 to 9, kind of looks pretty straight. And if you're dealing with a straight line, then midpoint rule, trapezoid rule, and the parabola rule or Simpson's rule, they all do a pretty great job. All right, so we started off the section talking about this really messy function that's used in statistics to find the area underneath a bell-shaped curve and to calculate probabilities. So suppose we wanted to know the area between -2 and 2 of this function. What does that look like? Well, it looks like a nightmare if you apply trapezoid rule, midpoint rule, or Simpson's rule, right? Can you imagine like having to plug that in and type it over and over again? But if we use fnInt, it's not too much of a problem. So I'm just going to copy that down. We want the integral from -2 to 2 of e to the negative x squared over 2, all of that divided by the square root of 2 pi with respect to x or dx. So on the calculator, fnInt, and then how would we type this monstrosity? Okay, so when you go to do the e to the negative x squared, you'll do e raised, and then you need parentheses, and you have to say negative, and you have to make sure you hit the negative key, not the subtraction key. X squared over 2 end parentheses. So you're making sure that the entire exponent is in parentheses so that e gets raised to all of that. If you don't have it in parentheses, you're not raising e to all of that, and we're supposed to. All right, and then the denominator, we do that by divided by the square root, open parentheses, 2 pi, end parenthesis on the square root. And then that finishes off the function, and then we'd say the variable is x, and the limits of integration are -2 and 2, and end the parentheses. So let's hop over there to the calculator and give that one a look. All right, so math menu below the alpha key. In the math column, number 9 is fnInt. It might not be number 9 on your calculator, just whatever it is for your calculator, you do want to learn that, or just make sure you're looking for it. Don't just press 9 mindlessly without checking to see that that's correct. If you look at the clear key, the key below that has an orange pi on it. The key below that has an orange E on it, and that E is the E we need right here. So second to get the orange, and then press that division key to get the E, and then I can do the raised to right above that. Then for the open parentheses, and then don't hit subtraction, hit the negative key, the one below the 3, and then x squared divided by 2, and the parentheses on our exponent divided by the square root of 2 pi, and the parentheses on the square root, and then comma, x is our variable, comma, -2 is our lower boundary, comma, +2 is the upper boundary. When I put in that lower boundary of -2, again, I have to use the negative key under the 3, not the subtraction key. All right, let's see if fnInt can solve our stat problem. Rounded to 4 decimals, that would be 0.9545. If you have taken statistics, you should recognize that as the area from the empirical rule, but underneath the normal curve within 2 standard deviations of the mean is 0.9545. If none of that made any sense to you, that's okay. But here we are able to calculate the area underneath a very messy curve very quickly, easily, and accurately using fnInt from our calculator. We're about to do some very messy definite integrals in some of the upcoming sections, and the algebra of simplifying can be a bit of a nightmare, or at least a tedious chore. So we're going to take advantage of fnInt to speed some of those up. So I think when we get there and we start using it, you're going to be glad we stopped by this section on the way. All right, that wraps up section 6.1.